Precision agriculture relies on continuous streams of sensor data, but network routing protocols behave very differently when the target is fixed in the soil versus when it is in motion. To collect this data, farms deploy wireless sensor networks. These are arrays of small, battery-powered devices that monitor everything from soil moisture to animal heart rates. Because these sensors have highly constrained memory and power capacities, they communicate using a specific networking standard called 6LoWPAN, running the RPL routing protocol. RPL was built to be highly efficient in stationary environments. However, when physical sensor nodes move, the protocol struggles to maintain stable network connections. To measure this exact vulnerability, researchers designed a comparative simulation. They ran a strict A/B test pitting a stationary network, an olive orchard, against a kinetic network, a stable of moving horses. Testing the limits of this routing protocol under kinetic stress allows us to determine if a single IoT architecture can reliably scale across an entire, varied agricultural ecosystem. This ecosystem operates on a proposed 3-tier architecture: devices at the bottom, communications in the middle, and applications at the top. If we isolate the middle tier, the communication layer, we find the core of the network's structural integrity. This layer translates data from heterogeneous agricultural resources, bridging it to upper-level servers. Within this tier sits the routing mechanism itself, the 6LoWPAN and RPL protocols. RPL builds a DODAG, a destination-oriented directed acyclic graph. Nodes map the most efficient path to the central sync node. Data flows in a specific, loop-free direction upward, cascading into the root. But physical movement breaks established parent links, forcing the graph to recalculate new pathways. While the sensors themselves and the upper application software continue functioning, the communication layer becomes the system's primary bottleneck the moment a physical node starts moving. To quantify this bottleneck, the researchers stress-tested the DODAG protocol using CUJA, an embedded operating system simulator for constrained networks. The test parameters deployed 36 standard sensor nodes feeding a single central sync node over a 4-hour simulated duration. The simulation first loads the mobility parameters, then enters a continuous logic loop, checking if sensor data is ready, formatting the packet, and triggering transmission. To see how distance affects the routing, the nodes were distributed across 4 different grid densities, scaling from a tight 25 by 25 meter square up to a sparse 100 by 100 meter area. To simulate unpredictable horse movement, the experiment used the random waypoint model. A node selects a random coordinate, draws a path, moves, pauses, and picks a new target. Speeds varied between 1 and 2 meters per second, intercut with random rest periods. By holding the node count, transmission rate, and grid size identical across both environments, the simulation isolates physical mobility as the exact variable causing network degradation. This chart compares the packet delivery ratio, or PDR, for static versus mobile nodes. PDR measures the percentage of generated data that successfully reaches the sync node, the clearest metric for network reliability. Stationary nodes maintained near-perfect delivery rates in the tight and mid-sized grids. Delivery only dropped significantly at the maximum 100 by 100 meter sparsity, where the distance between nodes caused some to become entirely isolated. But the Kinetic network failed dramatically in the mid-density grids. At 75 by 75 meters, while the static trees delivered 100% of their packets, the mobile horse nodes delivered just 55%. The root cause is speed. The RPL protocol cannot process route reconfigurations fast enough to keep up with the physical changes in the network. A fast-moving horse easily escapes its parent node's transmission range before the routing system can recognize the broken link and update the topology map. Because the graph cannot heal itself in time, the sensors blindly fire their packets into the void. The data is permanently lost. Standard RPL routing relies on stability. It is architecturally unequipped for environments where nodes frequently outrun their own network topology. This line graph plots data delay across the 4 grid sizes. This delay is the secondary symptom of mobile network failure, measuring the total end-to-end milliseconds required for a packet to reach its destination. Transmission delay scales directly with hop count, the number of intermediate nodes a packet must bounce through to reach the center. Nodes 1 hop away from the sync transmit data almost instantaneously. but nodes on the periphery might require 4 separate hops. Every time a packet lands on a parent node, it is processed and retransmitted, creating a compounding delay as the packet works inward. You might assume packing the nodes closer together would solve this by shortening the hops, but the simulation revealed a paradox in the tightest 25 by 25 grid. The delay actually went up. In hyperdense areas, nodes constantly spam the network with control messages to check for pathways. This crosstalk triggers massive packet collisions and intense signal congestion. Simply cramming more nodes into a smaller physical space does not solve mobile routing lag. It actively chokes the network with its own administrative traffic. These charts track the power consumption of our network nodes, mapping the percentage of time spent on active radio functions and their precise power draw in milliwatts. All of this network friction culminates in a physical hardware limitation. A sensor's battery life is dictated almost entirely by its routing efficiency. The baseline CPU and passive memory states consume less than 1 milliwatt of power. By contrast, the active radio functions, listening for incoming signals and transmitting packets, draw roughly 3 times that amount. Because mobile nodes must stay in these active radio states longer to hunt for parents and retransmit failed packets, they deplete their limited energy reserves much faster than stationary sensors. Projecting these power and reliability constraints back onto the 3-tier architecture defines the practical boundaries of the system. For stationary crop monitoring, standard 6-low-pan running RPL routing is a highly reliable, low-power solution that handles the environment efficiently. But for tracking kinetic targets like horses, standard graph topology lag makes baseline RPL unacceptable. The inevitable dropped connections cause severe data loss and shortened hardware longevity. To make precision IoT viable for mobile livestock, network architects cannot rely on off-the-shelf routing protocol for the integrity of their data.